Hey everyone, Alex here to introduce our next presenter, Dr. Ankur Chowdhary, who works as a cybersecurity engineer for Lincoln Heritage Life Insurance Company. He has worked for Bishop Fox and BlackBerry Limited security teams in the past, and his talk today is entitled, Can Artificial Intelligence Detect Advanced Persistent Threats? Make sure to stay tuned after the talk for a live Q&A. Just go ahead and click the link on your screen.
Hello all, my name is Ankur Chowdhary. This is my presentation on the topic, can artificial intelligence detect advanced persistent threats? So during next 45 minutes or so, we will explore the question, can AI in its current stage detect sophisticated attacks like advanced persistent threat? So a little bit about myself. I received my doctorate from Arizona State University last year, and I'm currently working as a senior cybersecurity engineer at Lincoln Heritage. I have been quite active in both academia and industry side of cybersecurity. I co-founded DevilSec, which is a hacking club at ASU. So if you do have time, please check it out. In past, I've worked for companies like Bishop Fox, BlackBerry Republic Services, and CSC Private Limited. Bishop Fox and BlackBerry are sponsors of this conference, so that's a happy coincidence. And this is my contact information if you want to reach out to me after the talk. So this is the agenda that I have in mind. So we'll explore like why do we want to use AI in cybersecurity, and in particular why at this point in time it is relevant. The next question I'll answer is, what is advanced persistent threat? We will also look at the cases which are not APTs. We will consider some APT stages and case studies to better understand the past APT attacks. Then we will dive into the motivation of this data set for advanced persistent threat that we created to benchmark the AI models. We will see how the state of the art AI models behave on this APT dataset. Then we will see the experimental results. And finally, I'll conclude the talk with some discussion for the future. So AI is an intelligent way of analyzing an environment by an agent and then updating its model of the world and taking better actions. So this is the diagram that you will see in most of the AI frameworks. And the agent in this case is trying to maximize his chances of achieving the desired goal. So why it makes sense to use AI in cybersecurity? AI mimics the cognitive function of human brain very closely. So we are trying to use AI models in many cases to mimic the stealthy attacks and identify and detect some of the methods that are used by modern attackers. Also, it can be used in cases of proactive cybersecurity where we are trying to deceive the attacker, and we are trying to play some kind of intelligent game with the adversary. So honeypots uh, are one of the techniques that is used, and there is research in the field of cyber deception where the defender is trying to identify the best response to the attacker's attack methods. So this is one example of how we can actively deceive adversary. And why does it make sense to use AI these at this point in time? So it's estimated, if you look at this graph, that in 2021 there will be 25 billion IoT devices, and the spending on cybersecurity will be around $1 trillion. There will be a shortage in cybersecurity workforce by 3.5 millions. And already 65% of the organizations are reporting that they have shortage of cybersecurity staff. And those organizations which do have enough personnel in the cybersecurity department, they uh, think that professionals are not trained enough to deal with the modern threats. So to manage this kind of complexity and this kind of workload, AI becomes very, very important. So next we will see how the National Institute of Standards and Technology defines advanced persistent threats. So these are a little bit different from our traditional attacks in the sense that attacker pursues his objective repeatedly over an extended period of time. And if you have defense mechanisms in place like your intrusion detection system or modern distributed firewall, the adversary is able to identify those defense mechanisms and adapt to them. So if you have, say, a endpoint detection system, the attacker can wait out the scanning cycle of that particular security product. And even if you are able to detect their current attack kill chain, they have alternate means by which they can maintain desired level of persistence to achieve their goal. So let's break down each component of APT. So what does advanced means? It means that these are not your everyday script kiddies. They are well-funded organizations. So if you look at some of the APT groups like APT 28 or APT 41, they are funded on a national scale. So they are basically really out there to get you. They use some of the attack tools and attack vectors, which you will not find on your traditional set of tools and techniques. And because it's at a scale of nation state, they are often trying to attack a high value target. For example, one of the APT attacks carried out against Sony was sponsored by North Korea. The next component is persistent. So as we mentioned in the definition provided by NIST, that they are motivated and they can gain back any connection attempts to their malicious software on your internal network, even if you disconnect it the first time. They follow evasive technique, which basically tries to evade any kind of detection system you have in place. So it's a slow and low approach. And it is called threat because it leads to the disclosure of sensitive information. For example, the data leaked about the healthcare information or credit card of a company can be a significant damage. The latest attack that we observed was the attack on solar winds, and it was a huge hit to their PR. It can obviously lead to disruption of normal operations in an organization, and needless to say, it's a big loss of reputation. And because these attacks use these kind of evasive mechanisms, the simple signature-based detection mechanisms used by modern IDS or firewalls, they are not enough to detect these series of events mounted by APT attackers. And this table shows that it has impacted almost all important sectors: automotive, communication, energy, banking. So it is very important that we understand the motivation behind these attacks and develop sophisticated means by which we can detect and block these attacks. So this is one of the ways of representing various stages of an APT attack. And this was something that we came up in our survey on advanced persistent threats, technique, solution, and challenges in IEEE communication surveys and tutorials. So we came up with this attack tree, which represents the different sub goals of APT, starting from stage one, where the attacker performs reconnaissance, gains initial foothold into the target organization, learns which systems are critical. Basically, it is termed as lateral movement, then perform some detrimental activity on one high value target and achieve their desired objective. And it is often followed by the post exploitation activities, which include deletion of logs and removal of any footprints that can help the defender organization trace the steps of the attacker. So if we look at these phases one by one, during the reconnaissance phase, the goal of the attacker is to gather as much information about the target organization, identify the websites frequented by the employees, their social media account, what sort of habits they are into. For example, if there is someone who is into fitness, it makes sense for the APT team to send a spam email to that person with some offer on some fitness drink. And this information can help the attacker move to the second stage, which is establishing foothold in the network. So during the second stage, the attackers basically compromise some known vulnerability or unknown vulnerability that they observed from dark web or deep web forums. They can also use business emails to send spam emails with malicious documents. And this helps them gain initial entry into one of the end systems or one of the edge devices or endpoints of the organization. And this leads them into the third stage, which is basically moving slow and low, evading detection, basically moving laterally in the organization and identifying some critical systems using this lateral movement. So using this lateral movement, the malware can spread into neighboring machines, some critical Active Directory systems. Some of the tools that have been observed include Windows Command Execution, Mimikatz, Windows Local Security Authority, and the attacker tries to identify some important nodes in the system. For example, a very critical FTP server or a database server, which has relevant information. So after the attacker has identified this information, they try to exfiltrate it to one of the command and control centers that they own. They can have Google Drives or FTP servers. And this step has to be carried in a manner that evades detection by the intrusion detection and prevention systems. So often they can exfiltrate this traffic over DNS, or basically they can use the batching of the data, basically distribute the data into small chunks, which basically fly low under the radar of that detection mechanism that has been employed by the target organization. And it often is an important activity carried out over a long period of time. So like the Sony hack that happened, the duration was around 140 days or so. So you can imagine the uh, any detection mechanism which is trying to identify these patterns. It's difficult for them to correlate the time series of these malicious activities. The last stage is that attacker uses some mechanisms to ensure that even if they are detected and blocked by the target organization, they can gain back that persistence, and they should ensure that they are covering their tracks to prevent any kind of forensic analysis, basically deleting logs. If there are dropper files by a particular malware, the goal is to delete those dropper files, those dynamic link libraries. And we will see an example of this nature where we will observe all these activities coming into play. So let's talk about one of the major breaches that happened on one of the credit bureaus in 2017, and it was claimed to be an APT attack. So Equifax was one of the largest breach, and it compromised the data of 143 million people. And attackers basically exploited an unpatched vulnerability that had a high severity score, uh, CVSS score, which is known as Common Vulnerability Scoring System, uh, for rating the risk associated with different vulnerabilities. So it was a high severity vulnerability, and that compromised the account of 143 million people. So think about this for a second. Is this an APT attack? So if the answer is no, you are right. This was one of the targeted attacks, and the attackers basically exploited a known vulnerability which was unpatched. They compromised the portal website, which had Apache Struts software, and this web server allowed them to gain access to database server and eventually exfiltrate the data to their command and control center. So a lot of times companies try to uh, shift the blame, claiming that something that happened is an APT attack, but in this particular case, this was not an APT attack. So if we try to differentiate between traditional attacks and APT attacks, the summary is that APT attacks are carried out by highly sophisticated organizations. They are well funded. Their target is very specific. For example, Sony or Equifax or any kind of nuclear facility in Ukraine. There was a compromise of the nuclear facility of Iran, known as Stuxnet. So their target is very specific, and their purpose is either to gain competitive advantage or gain a strategic benefit over the target. And their approach is not the approach of a standalone hacker, where the idea is to just show off something or use a smash and grab approach to basically show off to your friends, or basically compromise one particular component of organization. The attackers use a very slow and low approach. They adapt to the defense mechanisms in place, and the activities itself carried out over a very long duration of time. So let's look at the case studies of Hydrak, which was a APT exploit against the Google, which targeted a zero-day vulnerability, and later the CVE was assigned to this vulnerability. The attackers were able to successfully establish foothold in several organizations using this exploit. So this attack was carried out by using social engineering tricks and enticing users to uh, click on some links. And the zero-day vulnerabilities with these CVIDs had some JavaScript running at backend, which was basically obfuscated and hided the real intention of the attacker. The exploit targeted object handling flow in the HTML of Internet Explorer. So Internet Explorer was trying to access one of the deleted element, and the element was itself incorrectly analyzed. So when later this code was reverse engineered, the security team observed that binary shell code. So basically, if you perform a XOR operation using a particular key on the payload, you identify that the decoded instruction points to a installer executable, which is the shell code of a Hydrak installer. So what this Hydrak exploit does to maintain access is ensure that it uses a dropper file which generates a random service, and it drops a component dynamic link library from its resource at a particular location, and it adds this to one of the registry entries to maintain persistence. It goes on and creates a service with some characteristics which allows it access, which allows it to automatically start in case it is shut down. And this dynamic link library is component is executed under the context of generic host process service host.exe. Once the Hydrak is done with the exploit, it deletes its traces by removing the Hydrak dropper file from the list of registries. So the below registry entry, which we saw was used to maintain access, is deleted. And the dropper component creates a batch file, which eventually deletes the Hydrak dropper file. Let's have a look at another example of APT attack, which was the target breach that happened. So in this case, one of the vendor PC was infected with malware, and the attackers compromised its credential in step 1. They used the compromised credentials to connect to the main system, one of the vendor application server. So this shows that reconnaissance and foothold establishment involved exploiting the vendor PC and using it to connect to the main system of the target network. Because this vendor application was trusted, the detection mechanism in a target organization did not detect any or did not point to any lateral movement that was going to happen. So the attackers used this stolen token to create a fake admin account and propagated attack on the internal network. They went on and connected to some of the PCs with the fake admin credentials. So this shows that lateral movement happened in step 3 of this exploit. They infected the internal systems on the target organization and installed malware on some critical systems with the goal of exfiltrating data out of the target organization. And eventually they used FTP as a mechanism to send the stolen data over network share to their remote command and control center. So this shows you that there are 4 or 5 stages in an APT attack. So there is also post exfiltration and deletion of logs, which is part of APT attack. But in our research, it's not very important because it does not add further value to our machine learning models that we will discuss as part of this research. But these 4 stages will be important, and we'll refer to them throughout the next phase of this talk. So we have seen previously in like a last few slides that APT attacks are very difficult to detect. So another reason we went on and created this data set for APT detection, DAPT 2020, was that we wanted to benchmark if the current AI models are good enough to detect APT attacks, and the data sets that these AI models train on to claim that they are getting 90% detection accuracy or 100% detection accuracy. Are those data sets themselves good enough? And as a snapshot of what we are going to see next is that existing data sets fail to model all phases of APT attacks, and they don't cover all the attack vectors of the APT attack. So we try to provide coverage of both of these when we generated this APT data set. So we created a system where we had the gateway router providing access to a public virtual machine which had some vulnerable softwares, for example, Mutility AI or DAM vulnerable web application, bad store, meta exploitable. And the red team was asked to first compromise the service on the public machine, then move on to the private virtual machine, which was hosted on the internal private network. And after compromising the private virtual machine, basically exploiting these services like Samba, web application, or WordPress, their goal was to exfiltrate the data to their command and control center using any mechanism like secured copy or SFTP, or using a client to exfiltrate data to the Google Drive they created. We used Elasticsearch, Logstash, and Kibana, basically ELK stack, to record the host log information and network packet capture, which helped us record the network and host activity of the red team during the duration of this dataset creation. So you can see different networks, the FileBeat, which is a component of ELK, or basically agent of ELK, which helps collect this logs, is on an API network, and the private network connects the public VM, private VM, and log server. And the red team was using the exposed service on the public network to access the public VM first, and then eventually leading up to the goal of private VM and exfiltrating the data. So what we did was we broke up the APT attack across multiple days. So during day one, we asked a group of students to perform the normal activities on these services that were exposed on public network. So they did ping, get, post requests, they pulled web pages, they used curl to test some of the links on these vulnerable services. They uploaded the files, downloaded the files. So this was done to baseline how the normal behavior of the users looks like. During the second day, the red team performed reconnaissance using different tools and techniques, such as Burp Suite, or they used account discovery techniques or SQL map. The idea was to cover as many TTPs as possible. Once they had the reconnaissance information, the next stage was foothold establishment, where the red team basically used things like PHP reverse shell or netcat or SQL injection to exploit the vulnerabilities on the public VM that we can see in the top left of this figure. And the idea was to gain root access or gain some kind of persistence on the public VM of the network. So during next day, they use lateral movement to target the services on the private VM like Samba or DNS. So these were a little bit difficult to target compared to the services on the public virtual machine. So they performed Nmap scan, they exploited some authentication and used authentication vulnerabilities and used some scripts to target the vulnerabilities on this private network. And on day 5, they used tools and techniques like Google Drive client to exfiltrate the data, or using FTP to exfiltrate the data to their FTP server, or simple tools like wput or SCP. So uh, as you can see that we did all the individual activities during these different days to ensure that we can observe each individual activity of the APT attack that we defined during the example of this target hack. So that was the motivation to perform them on different days. Another key thing was that we carried out a lot of normal activities during that these days, and large percentage of traffic was normal activities. So this was done to ensure that the percentage of attack traffic remained very low compared to the normal traffic. So we had the student team doing the normal activity during all these days, and the red team trying to do these attack steps and trying to blend in to the normal traffic. So when we compared the data set that we created, DAPT 2020, with other data sets, we observed that most data sets, they perform only first three phases of APT attack. Like CIC-IDS was a well-known data set that performed just normal traffic reconnaissance and foothold establishment. Similarly, other data sets that are popularly used to benchmark machine learning models, they were missing the lateral movement and data exfiltration, which was carried out in our data set. So this was to provide completion of all phases of APT attack. So next I'll discuss the machine learning models. So the idea was to use semi-supervised machine learning models, and by developing a baseline of normal behavior, any deviation from this baseline behavior was indicative of the anomaly. And semi-supervised approaches are prevalent in anomaly detection research, where the idea is to make distinction between normal and anomalous traffic when the large percentage of traffic is normal and only small percentage of traffic is anomalous. So semi-supervised models perform well in those scenarios. So one class support vector machine are known to be particularly effective in scenarios when there is a large percentage of normal traffic and small fraction of anomalous data. So the idea is to train the model on labeled example of class with more data, and any deviations from that are anomalous. The stacked autoencoders are specific type of feed-forward neural network that find the compact latent space representation of input, which can be later leveraged for reconstruction. So autoencoders have hidden layer, and there is basically compression operations that occurs between the input and hidden layer. And they use the notion of reconstruction between the hidden layer and output layer. So the compression function in the stack autoencoder is followed by reconstruction. And this is done with a deep neural network as opposed to a single nonlinear layer in other uh, neural network neural network frameworks. The output of stack autoencoder is then uh, forced to basically mimic the input, and the loss function seeks to minimize the distance between the original input and reconstruction output. So what we do is we first train the stack autoencoder on normal traffic, followed by testing it on both normal and anomalous data. The expectation is that although stack autoencoder can correctly reconstruct the normal data, it fails to do so effectively for abnormal data. So basically, the data with high reconstruction error can be flagged as anomalous. But the stack autoencoder is limited in the sense that they are not capable of detecting contextual anomalies, which uh, are significant in advanced persistent threats. So basically, we use long-term short memory stack autoencoder to use this time series correlation between different phases of APT attack. This is because the input layer of stack autoencoder only accept a single network packet as input, and stack autoencoder that uses LSTM cells instead use hidden layers uh, as the LSTM cells instead of like a single neuron, which is in case of stack autoencoder. So this helps in the use of basic cell as LSTM, helps in successful time series analysis. And this modified stack autoencoder is known as LSTM stack autoencoder. So this compresses the network traffic packets in multiple time series steps and then basically reconstructs those. So this is the information on data that we collected. We collected network traffic data, which comprised of syslogs, DNS logs, access and authentication logs, the logs of SQL servers. And we used PCAF files, and we basically extracted 84 features from the network traffic data, such as flow duration, the total forward packet rate, the total backward packet rate, the inter-arrival time between two flows. So we used different measurement metrics. So first one was precision recall curve. The precision is true positive divided by total data, basically the true positive and false positive. The recall is true positive divided by true positive plus false negative. And the reason we used PR curve is because the attack representation is often very small fraction of the total data. So it will be around maybe 2% of the total data set. The ROC, area under curve receiver optimized characteristics, receiver operating characteristic, basically uses the false positive rate in comparison to precision used in PR curves or precision recall curve. The issue is that false positive rate is less sensitive to changes if the number of false positives are very high. So basically, normal traffics being classified as attacks is one case of false positive, whereas the precision looks only at the class of positive samples, which in our case is basically anomalies. So it provides a better metric when particular class is severely underrepresented, in our case, the APT attack phases. So performance of algorithm on different data sets using accuracy or ROC curve can also become a little bit misleading in the context because they have different percentage or degrees of anomalies. So one observation was that the attack traffic in CICIDS is 22%, whereas in the case of UNB 2015, the attack traffic was around 14%. So we use another parameter, basically confidence value P, after normalizing the reconstruction error across the test sample between 0 and 1. And when the reconstruction error is large, the value of P is close to 1. Thus, P indicates the confidence with which the model predicts input as anomaly. So to plot the PR curve, we first set a threshold value. We then use the test input and find how the value of this confidence interval is compared to this threshold. If it is above the threshold, we classify it as anomaly, and if it is lower than threshold, it is normal. So ideal classifier should be able to predict the test label of each input with complete confidence. So if there is an anomaly and the classifier is doing well, the value of this confidence value P should be 1 for the normal traffic, and it should be for the anomalous traffic, the value of P should be 1, while for the normal traffic, it should be predicted as 0. And we also used a baseline no-skill classifier that outputs value of the confidence interval 1 in all cases of input data. And it is shown in the plots that follow using dotted lines. The abundance of attack data in one phase helps the accuracy of overall anomaly detection system, which may be highly unreliable in some other contexts. So that is the reasoning behind these metrics that we used. So we observed how these different AI algorithms, Stack Autoencoder, LSTM, and LSTM, Stack Autoencoder, and SVM perform. So Stack Autoencoder performs satisfactorily in two settings, that is detecting reconnaissance attack on CICIDS 2018 and detecting foothold establishment on our dataset if you look at the bottom right. In case of reconnaissance, the anomaly detection uh, performed by Stack Autoencoder works well only for CICIDS 2018. And for this case, the no skill classifier has a precision value 0.23 corresponding to the anomalies. And the no skill classifier is far better compared to other data sets with the far better than any of the other data sets with the high precision value of 0.87 for some threshold. In case of foothold establishment phase, the Stack Autoencoder behaves very unsatisfactorily, and it is as bad as no skill classifier. And the lateral movement and data exfiltration were not in some of the other data sets. And on DAPT 2020, Stack Autoencoder performed very badly for these two stages. In case of LSTM Stack Autoencoder, there was a significant improvement in reconnaissance phase. The performance or maximum precision value increased to about 0.9. This is to an extent an indication that there exists some contextual information, particularly in case of CICIDS 2018, that is detected by LSTM Stack Autoencoder. For the foothold establishment, the performance is as bad as a no skill classifier for LSTM Stack Autoencoder, and it is bad for other datasets as well. The performance of the LSTM Stack Autoencoder on our dataset, because no other dataset had lateral movement and data exfiltration, was much worse compared to Stack Autoencoder. So lastly, in case of support vector machine, in reconnaissance phase, the learning classifier performs as bad as no skill classifier for all dataset except CICIDS 2018 that you see in the red line. And it's performed quite well compared to their previous dataset CICIDS 2017 and UNB 2015. It essentially implies that like for CICIDS 2018, there were a lot more reconnaissance attempts compared to other datasets. The foothold establishment phase is one case where support vector machine performed well on our dataset DAPT 2020 compared to other datasets. For most of the other datasets, it's as bad as the no skill classifier. And for the lateral movement and data exfiltration, Support vector machine performed very poorly on our dataset. So next we did some observation of different phases of APT attack, reconnaissance, foothold establishment, lateral movement, and exfiltration using the receiver operating characteristic. So area under curve ROC and area under curve PR. So these ROC curves represent the true positive against false positive, and the graphical or the table illustrates the diagnostic ability of the binary classifier for varying degree of threshold. So AUC-PR summarizes the curve's precision against recall, and AUC-ROC is the value. So AUC-ROC value, when it is close to 1, it implies that it's good performance, whereas if it is close to 0.5, it means it's making the classifier is making random guess. AUC-ROC is good for interoperability. However, if anomaly detection mechanism is sensitive to performance on the positive class as opposed to negative class, AUC-PR is a good metric for anomaly detection. So we can see that for reconnaissance, the AUC-ROC is detected very well by Stacked Autoencoder on all datasets. The Stacked Autoencoder LSTM does well on the CICIDS 2017 compared to other data sets, but it's not a regular pattern. The AUCPR values were consistently low on all data sets. In the foothold establishment phase, Stacked Autoencoder showed better performance compared to other AI models, particularly in case of DAPT 2020, where the value was 0.846 for the foothold establishment AUC ROC. In case of lateral movement and data exfiltration, the AI models consistently performed badly. So they achieved low value for all unsupervised learning algorithms. And it shows that attack vectors employed in our data sets were highly stealthy, and the AI models were not able to detect them accurately. So in conclusion, the reliable detection of APT attacks is a very challenging task. So we did our best to generate a dataset DAPT 2020, which covers all the phases of an APT attack. We showed using state-of-the-art semi-supervised machine learning models that these attacks are very stealthy, and these models do not show consistent detection of all phases of APT attack on these data sets. So we need to develop some better AI models for APT detection. So if you want to have a look at the data set, it is hosted at this location. And with that, I will conclude my talk, and I can answer any questions. Thank you.